Hello. All right. So since last time, I've done a lot of reading over the break. And I have a pretty good idea of how to do the next few steps. So just to recap where we are, right now I'm a few minutes into training this network. We've got a layer norm at the beginning, a linear layer that converts a one hot encoding of a character by character of an input prompt into a vector that's number of characters times number of possible characters length. Then I'm putting it through a bunch of linear layers that are really small, so 80 neurons each, with some nonlinear layers in between, so ReLUs, and I've got a few skip layers in between. So we've been training for like 5 minutes. I'm gonna kill this and type hello. And we've got something pretty good after 5 minutes of training. So that's where we are now. I'm going to stop that. The thing we're trying to build is a transformer. One of the things So I've been doing a bunch of, where we last stopped, I didn't know what we had to do next. Since I've been doing some reading over the break, I have a pretty good idea of what we need to do next. So the blocks that we have implemented already here are the softmax on the output layer, linear layers. We've got add, which we're calling skip. We've got norm, which is layer norm. Feed forward just means linear layers with non-linearities in between. So we've got that. Then there was some stuff that I was not super clear on. So attention was one of them. There's 3 different kinds here. The positional encoding was something else I was not sure about. The way that the inputs are encoded or embedded was a mystery to me. And what is the purpose of these 2 different columns? I didn't understand either. So here's what I learned in between. You can make a transformer that only has this right side. It's called a decoder only transformer. And that's what GPT is. So I'm going to just stop thinking about the left side. I don't need it. My understanding is the left side is for when you're doing stuff like translation, where you need to keep a big context in mind while you're outputting stuff piece by piece. But if you only have the right side, you can do what we're doing here, which is like, I also learned the word for this. The word for when you take the output and you put it back into the input 1 character at a time is called autoregressive. So we don't need this left side to make a transformer. We can make a transformer with only this right side, which means you can drop this middle part of the decoder block. We don't need the attention block that combines the decoder with the encoder. So we only have 2 little blocks in here. We'll have the 1 attention block that goes into a feed forward, and that'll be our block that gets repeated. Positional encoding. My understanding of this right now is that we know the positions of the characters in our prompt right now because it's the way that the vector of inputs is made is it's just the first character followed by the second character followed by the third character. But my understanding is once we put it through the first layer of attention, the attention will destroy the positional information and we'll be left with like a bag of letters and we won't know which letter is in which order. So the positional encoding is something that you do before the first attention block so that it the information about what order the letters are in is preserved. And I don't super understand that yet, but that's okay because we've got other stuff we can do first before we get to that. The inputs, this is another big thing. So right now, the way I'm doing my inputs is I've got a really big vector. So if my input is hello, it's going to look something like this. Oops. How do I add words here? This will be the H. This will be the E. This will be the L, etc. And then this is like 0. Ooh, didn't mean to do that. 0, there's a 1 somewhere. It's a 1 hot vector. And then this has a 1 somewhere else. And then this has a 1 somewhere else. Right, so this whole thing is a 1 by like alphabet size times prompt size vector. The thing I've learned about transformers is, oh, and then once we, here, can I just draw? So, here, I'm going to draw a square, and the reason I'm drawing it in this weird way will make sense in a second. No, let me do it this way. So here we have text batches, and on this side we have samples. Can I rotate this? I don't know how to do that. Here, samples. Right, so each column is a prompt and they look like this. They're really long columns and they're by 1, and then we make a matrix that has 50 samples, and then we do matrix multiplication all at the same time for our forward and backward propagations. So the thing I learned is that the way other people do this looks like this. So it's not a matrix, the input is a tensor. And here we've got batches. Here, or let's keep it the same as before. This will be batches. This will be samples. Well, actually, we have to. So samples is gonna be the thing that gets split into 2. So why don't I call this batches? I'll call this. I'm just gonna write all 3 of them. So it's like sequence, and then the other one is called, I actually don't remember. Sample, maybe? Maybe it's still called sample. So yeah, so I guess if I look at basically a single sample for me now is going to be already a matrix, and then a batch of samples is going to be a tensor of three. I don't even know what you call it. A three tensor, a tensor of order 3. So instead of calling it sample and sequence, what do people call it? Sample, sequence, batch, tensor. I don't know what people call it, but I'm just going to call it so a face is a sample. A face here is a sample. Here, this is going to be, I don't know how to say this, but it's like one of the dimensions is alphabet size, the other dimension is prompt size. Yeah, I don't know how to say that. Maybe I'll call this token, because we're going to upgrade from characters to tokens eventually. Token sequence batches. So each column is a token. A face on this side is a prompt. Maybe I can call it sample / prompt. It would be the front face. Okay. So what was the point of this? The point is we're going to have to change our code to take tensors as inputs, and make sure that everything still works with tensors as inputs. It should make some stuff more efficient, I think, because our dimension on this axis won't be so big, so our matrices, like this layer, should be a lot smaller, because this side will be 87. How do I say it? It's like 87 would be the token dimension, and it would not have a character dimension, so it wouldn't have that. Each character is kind of handled separately. So hopefully that made sense. I'm not sure how much sense I made. But okay, so here's the goals that I have. The first two are things to do that should hopefully be pretty quick before we get to upgrading all of our code to care about tensors. So softmax, if you recall, we tried to implement a softmax layer with a backwards pass. We actually don't need the backwards pass in order to do this softmax layer, because it combines with the cross entropy loss function to cancel out. But we do need the backwards function if we're going to have a softmax in the middle of the network. And we do need a softmax in the middle of the network to do the attention block. So decoder only attention. Let's see if we can find a good image. Here. For example. So linear, this is what an attention block looks like. You've got linear, which we've got, matrix multiplication, which we don't have, that's on the list, softmax, which we have, but I'm not convinced that we implemented it properly for a reason that I'll get into in a second. We need to be able to concatenate, so that's on the to-do list also. And we need to be able to, they call it multi-headed attention. We need to be able to split our input into multiple attention heads. So we split it, we do a bunch of separate attentions, and then we concatenate them together. So we need multi for splitting and concatenating for concatenating, and matrix multiplication for matrix multiplication. And then softmax, which I think is not working properly, and let's get into that now. The reason I think it's not working is we just saw that when I trained this network, after the first epoch, we were at 50%. Here, if I put a random softmax in the middle, so let's replace this ReLU with a softmax. Last time I did this, it gave us closer to 16%, and I said, well, I don't know if that's working or not. Well, we're getting overflows now, so that's, I guess, even more evidence that it's not working. But even without the overflows, I just wasn't sure how much it was supposed to help or harm to have a softmax layer right in the middle of the network. So I said, let's just put this off until later. And now it's later. And now that I've thought about it some more, I think it should not have a big impact on the network to put a softmax in the middle. It's kind of a way to do a norm or a nonlinearity. It should kind of not have that big of an impact in my my intuition is that it shouldn't have that big of an impact because it keeps the, well, here it just killed it completely, but I think that's because of the overflows. Yeah, we ended up with some infinite stuff. I'm not sure why that happened. Will that always happen? Maybe. What if we add a norm right before to make sure that the inputs are not that big? This should just be 80. Anyway, my intuition is that changing the sizes but keeping the relative order of the sizes is which is what the softmax is doing. The largest output will still be the largest output. The smallest output will still be the smallest. We're just rescaling stuff. This is basically a way of scaling like layer norm, and it shouldn't have that big of an impact. Here it's just like completely not working at all, which is not what I remember seeing before. I thought before I thought before it was working, but it just brought us down to 16%. What if I added layer norm instead of a ReLU here? That seems to be okay. And I'm guessing this won't have a huge impact either. Let's see. Wish I could get faster feedback. So I'm expecting somewhere around 49%, like 1% worse than having a ReLU there. Guess it makes sense to be slightly slower because layer norm has some learnable parameters, whereas ReLU doesn't. There's a bit more work to do here. $49. My intuition was spot on. Hey, counting that Warus Sirs Kindmal you for Reitil her Quickle even was you never. 6 up. Yeah, Whaley. I cutted. Very cool already. Okay, let's bring this back to a ReLU. Well, no, let's bring this back to a softmax, which was not working, and we want to get it to work. And I think it should work, and I think it should bring us to around 45%. Should be a little bit worse than using a ReLU here, but it shouldn't wreck everything. So, softmax. We know the forward is working properly because we've been getting good results with softmax on the end of the network. I suspect this backwards is not implemented properly. I don't remember how I got this. I think I may have just asked Gemini to do it and then either didn't understand what it told me to do and implemented it wrong, or it made a mistake. But I've been Googling how to figure out the backwards softmax. And the basic trick, and I think this actually applies to every backwards function, is to find the Jacobian matrix, which is the derivative of everything with respect to everything else. So it's a square because one axis is the derivative of everything and the other axis is with respect to everything else. So the Jacobian for the softmax looks like this, where H is the softmax. So H is like the activation, the output of doing a softmax. Delta is the Kronecker delta, which just means it's, let me zoom in here. It just means this is 1 if I equals j and 0 if it's not. And then yeah, hi and hj are just indices into this a. So that's the Jacobian, and then you just multiply the d. That's what sigma of L plus 1 is representing, by the Jacobian, and you get the activations of the inputs. And then there's the special case of if you're the output layer and you're using a cross entropy loss function, then you can just do this, which is what we have been doing. But let's comment this out and see if we can implement it using the Jacobian directly. So J is going to be a matrix whose entries are defined like this. I found this blog post that shows it visually also. So, oops. the off diagonals are products of indices of the softmax and the negation of that. And the diagonals are that, but plus imagine stretching out the activation into a diagonal and adding it to that matrix. So basically it's I think it's actually like D transpose. No. S of I is the activation. So A transpose matrix multiplied by A and minus that. That gives us the off diagonals and part of the middle. Then to that we add A, but as a diagonal matrix. So something like that. NumPy diagonal matrix from vector. Wouldn't you know it? np.diag. Yep. So that is this. I think I can make it one character shorter by putting it in the other direction. And then delta is just J matrix multiplied by D. What are the odds? What are the odds that that works? Let's see. Maybe you're wondering how I, okay. $80 is different from 50. So activations should be 80. There should be 80 activations. So this should be an 80 by 80 matrix. I would expect D to also be an 80 by 1 vector. Print J.shape, A.shape, D.shape. Okay, I thought everything would be 80. J.shape ended up being 50 by 50. Oh, I forgot that these were matrices. Okay, I think that just means do it the other way around. A matrix multiplied with A dot T. If I'm getting the wrong dimension. So what is this? It didn't even print this time? Oh, because I'm trying to print after doing this, but this is already not allowed. I guess I can't just do diag of A because I was thinking of A as a vector, which it is when there's just one. But it's not a vector once we start using matrices, and it's going to be even more not a vector once we start using tensors, like order 3 tensors. Um, how do I fix this? I guess I want my Jacobian to be an order 3 tensor here, even when I'm using matrices as inputs, with the batch dimension going the other way. But that gets pretty hard for me to think about. Okay. All right, well, I gotta figure this out, I guess. The problem is I don't really know how to do tensor stuff yet. In the end, delta is just going to be a matrix, but the Jacobian is an order 3 tensor, and delta is a matrix. So I'm going to have to do like order 3 tensor matrix multiplied by matrix. The order 3 tensor, I kind of get what it looks like. It's this, but one of these for each batch. And I guess I just don't know how to write that really. So if I wanted to start with the off diagonal entries, it would be like it's something like tensor product of A transpose and A, right? Because I want every pair Okay, this is probably where I can start using Einstein sums. So the two inputs are A and A. The first A has indices ij. The second A has indices ij, kl. And the output is supposed to have, well, okay, so I batch let me just print a.shape, d.shape again. Whichever one has 50 is the batch. Whichever one has 80 is the other one. Okay, 80 by 50. Okay, so the first thing is some index and then batch, and then for the next one, j and then batch. And then the output should be like ij batch. There should be one for each. It should be an order 3, and there should be one cell for each I, for each j, and for each batch. So this is going to be what j is equal, or this is almost j. This is the off diagonals of j. So then we need a minus on this. And then we have to add the diagonals to this. So for each how do I say this? For each batch, what can I use? I bet I can use einsum for this also. It's so the two things that it's going to take are j and a, and then you've got ij batch is the first thing. The second thing just looks like I batch, and the output is still ij batch. That's the right sizes, but is this going to do the right thing? That I'm not sure. These are the off diag. What will this actually do? So IB I don't think this will work. I think that's going to add it to everywhere, not just to the diagonals. What I would need is to say something like IIB or something, but I'm not like comfortable enough with Einstein summation to know how to do something like that yet. So the diags are going to be it's like for each batch add diag of A. I don't want to write it like this, but for call in or for I in range D dot shape of 1, because that's the batch dimension. So for each batch, call it a bat for B. J of that batch, but then I have to have the right index. This is stupid. I'm not going to do it with a loop. I have to just figure out the right way to do this. I'm just curious, because this should already be the right shape. So it shouldn't work, but it shouldn't crash. Like it shouldn't give a good percent, but it shouldn't crash. $80, $80, $50. That's what I was looking for. But I can't do a straight matrix multiplication unless I reshape D, probably. To be D dot shape and then a 1 on the end. Am I allowed to do it like that? $80, $80, $50. I guess D is 80 by 50, so it's not putting a 1 on the end, it's maybe putting a 1 at the beginning. I should just do an ein sum on here instead of trying to force a matrix multiplication. Ein sum J and D, where J is IJ batch, D is I, or we'll say K, and then we'll figure out which ones need to be joined. K batch. And then the result is supposed to be K batch. So I think this should be J, this should be J. The I ends up going into the summation. Is this possible? This is my first time working with ein sum, so I'm really not comfortable with it yet. Okay, it's not crashing, which is good. But we don't expect it to work well. Because we don't have the diagonal entries. Okay. It's crashing, but because the numbers are getting crazy, not because the dimensions are wrong. So now we have to add the diagonal entries. Which I know you can do with ein sum. Or I bet you can do with ein sum, is what I should say. So IJB so the batch should be the same for both of these. And then I think it's like, it might be like this, IIB to IB. No, because I don't have the J. Maybe I can't do it with ein sum. How do I do this without a for loop? For B in range. Shape -1, so 50. J of this batch, except it's not the first index. It's like, am I allowed to do this? Plus equals numpy.diag of A of the batch. I think this I think this is right. It's just crazy. It's not a good way to do it. Oh, and it doesn't like it. 80-50, 50-50, 80-50. Why is there 3 things here? There should just be the left side and the right side. That's weird. I don't get it. I don't get why there's a 50-50 in the middle. Because this should be a vector. I guess we just need to print everything, every shape. Print your shape, print your shape, and print your shape. $80 by $50. Is not what I expect. I wanted 80 by 80. I want to be choosing the 50 dimension. And then this guy is 50, which is not what I wanted because I want to be choosing the 50. So let's play which dimension is the 50 dimension. Let's try the first one. $80 by $50. Wait. $80 by $50, $50, $50 by $50. It didn't even matter? Why does it not matter which slices I take? I'm getting stuck on something stupid. Let's Google this. NumPy add diagonal to tensor. NumPy.fill diagonal. Or diag, which we're using, or diag flat, which I don't know what it does. Fill the main diagonal with a scalar value. That's the same as doing .diag, right? Fill the main diagonal across the last two dimensions with an array-like value. What does that mean? It didn't really explain. IJK, JK becomes IK. That's what I'm doing here. Kind of. I got, maybe this needs to be IB actually. sparse matrix vector multiplication between a block matrix of diagonal blocks. No, that's not what I'm doing. But fill diagonal kind of seemed promising. Repeating if necessary to fill all diagonal entries. So if you put the same thing, if you put just 5, it puts it in each place in the diagonal. This is doing it along a different type of diagonal, like a diagonal. I don't know. Put mask. Yeah, this kind of seems promising. How does this even work? X is a range. Put along axis. I don't know. To each matrix in a 3 tensor. This is what I'm looking for. Yeah, I want to add different vectors to the diagonal of each matrix. So I've got my diagonal vectors, let's say. Okay. This looks like kind of what I'm doing here. But my slicing thing was not working. Maybe this will work. Diag indices and numpy.diag indices n. Okay. So we've got a tensor 3D. We're going to call this J. What is the 1 here? I'm not sure which thing it's supposed to be. Maybe it's supposed to be the last one, because that's our batch dimension. Or maybe it's supposed to be the first one. Not sure. So then we've got diag indices. This is J. Then we've got diagonal vectors that we need, which are what? It's diagonal vectors is actually just A. It's actually just A. So it should actually be this. Index 50 is out of bounds for access to, okay, so maybe we try this. It's not failing, which is unfortunate. Because it's overflowing, but that's going to make it hard to tell what the problem is. It's also, is it stuck or is it just taking a long time? Oh, it's just taking a long time. And now I'm expecting 1% because it probably totally didn't work at all. Yeah. Well, that's too bad because I don't really know where to start. I mean, it can't be this because this will be the wrong. Well, that might be the same thing. I'm actually not sure. I'm not used to reading Einstein sums, so I don't know if that will be the same thing. I guess one thing we could check is J symmetrical, because J should be symmetrical if we did everything right, right? Well, along each batch it should be symmetrical. They don't make it easy. Oh, that's kind of cool that it pasted that copyright notice thing. So J of 0 should be symmetrical. Oh, well, I don't know what J of 0 is actually, because I don't know which index is which. That's like a really big problem. Can I just print J? Is it possible that I could be able to read it. Na 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 na. Okay. I mean, that helps explain why it's not working. How did that happen though? Are they getting smaller and smaller? Probably because I'm doing something wrong. But looking at J is not helping that much. 80, 80, 50. What about J of 0? Which index am I grabbing when I do that? The first one, as expected. So slice, slice, 0. I expect this one to be 80 by 80. It's 80 by 50. That's, I don't understand that. But I guess you just can't do slices the way I'm trying to do slices. None of those were 80 by 80. NumPy, slice, array slice. Oh, maybe the things I was doing before would work. It's just that I have to put all three. I have to do it all in the same index. I don't index and then index the index. I just have a tuple inside an index, kind of. Okay. So this is 80 by 80. Now I want to look at how symmetric are you? Check symmetric. J of colon, colon, 0. Because if I did it right, it should be symmetric. Not symmetric, so I didn't do it right. Okay. What about before I tried to do the diagonal entries? Is this symmetric? Right. No. It's already not symmetric right off the bat, which seems weird. Right? Like, how could this not be symmetric? Print J of 1, 1, 0, and J of not 1, 1. Print me 0, 1 and 1, 0. So those should be the same number, because they should be softmax of 0 times softmax of 1. These should be commas, not nan. Oh, they started symmetric, and then once they became nan, once it overflows and it becomes nan, then it stops being symmetric. Okay. And we're not symmetric as soon as I try doing the diagonal thing, which should not affect the symmetry if I'm doing it properly. Okay. These are not the right indices. The last one should be a slice. These can be the first two. And this could be either 0 or 1 because it's symmetric at that point. No, I really thought that was going to work. Okay, did we start symmetric? True, 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 true. Okay, we do start symmetric. But our gradients become so tiny. Okay. Hail Mary. Changing that I to a J in the einsum at the end. Nope. Yeah, the gradients get tiny right away. But at least we're symmetrical now. I mean, now that it's symmetric, it's hard to figure out what I could be doing wrong. So Python import numpy as np dot array 1 2 3. Let's say A is that. Then we're gonna do no, let's make A be one, two, three, 2, 3, or I just want to make a, let's just do 1 2 3 1 2 3 1 2 3. Okay, so A is this. So it's like for each batch, it's the same. Actually, let's make it not symmetrical. A dot shape. A equals A transpose. a.shape. Okay, so we'll say there's 4 batches, and each one is 1, 2, 3 is the activation. Then let's do negative np.einsum ib jb goes to ijb. And then AA. So there's 4 batches, so I should look at the columns. Let's just call this J. J equals this. J dot shape is 334. So let's grab the first batch. What's wrong with doing this? Oh, I don't want dot shape. Grab the first batch. This looks right. These are the off diagonals. It's the product of each 2 things. And in the bottom, it's 3 times 3. This is 2 times 2, 1 times 1. Negation of that. So the J looks right so far. So I think this is good. Then what's np.diag indices of j.shape1? Okay, it's just got it. So let's say indices equals np.diag indices j.shape of 1. I spelled indices wrong, but it's fine. Then j of indices 0, comma, indices 1, comma, slice. These are going to be the values to replace, or like add a to. Because if you multiply these out, you get negative S1 times S1 plus S1. So we're just adding A, you know, A1, A2, A3 along each diagonal. So we do this plus equals A. Now we take a look at J. Let's take a look at this guy. So we should have added 1, 2, and 3. So this, it looks like we did, because last time we printed this, -1, -4, -9, 1 plus -1, 0, 2 plus -4 is -2, 3 plus negative 9 is negative 6. So I think we're doing what we're trying to do. So even this looks right so far. Should be the same for all of them. Then this last einsum is the last place where we could be screwing it up. So D equals NP dot array. 4, 4, 4. Let's just do 2, 2, 2, 2. 4 batches, and they're all gonna start the same. Then we, like, what I want to do is just this, but you can't, I guess you can. And is that going to be the same as doing np.einsum ijb, jb goes to ib, jd? D dot shape, A dot, oh, okay, D equals D transpose, and then try that again. This is different from doing the matrix multiplication. But this looks like it's actually the right shape. So J of whatever 0 is that, and then this matrix multiplied by D of whatever 0 is that negative 10, negative 20, negative 30. So this einsum looks right. Well, I just double checked everything and everything looks like I'm doing it properly. So why is it not working? Why is it working? Or why isn't it working if I have checked every line and every line seems to be doing what I want to be doing? Um, don't get it. I've got the Jacobian. I have the Jacobian. I'm pretty sure I did the Jacobian properly. Pretty sure I'm multiplying by the deltas properly. Everything goes directly to 0, and then everything's not a number. Well, why is it becoming not a number instead of just becoming 0? Yeah, why is it becoming not a number? So where am I printing the not a numbers? Would it be here? So I guess it's becoming infinite. Some of the numbers are becoming infinite. Oh. I don't think it's this actually, but could it just be that I have to normalize stuff after a softmax, otherwise things diverge? Or possibly before. Let's do it before and after just to be safe. No, I'm still... Really not sure why stuff is diverging. because this trick where you remove the max should prevent the diverging in the forward pass. And then the backwards pass is just multiplying things. Like, it's not doing any divisions or anything that could diverge. I don't know. I don't really know what to try next. I don't see anything that should make anything diverge in this. I don't know why putting a softmax here would make one of the other things diverge. Well, actually, maybe you're not supposed to do this max thing. On an inner softmax. No, it shouldn't matter. It should give the same answer. Print D of 0, A of 0. Or wait, these are 2D. So my J's start as -11. My D and my A start as -1 and 5. Then we go all the way to 10 to the 21, negative 10 to the 21, negative 0.7, and huge number for my activation. How is my activation big? Shouldn't my activation be between 0 and 1 for a softmax? I would think it should have to be between 0 and 1, but maybe this trick of subtracting the m is making it big. I'm pretty sure something's going wrong because my activation is larger than 1, even on the first iteration. I mean, what if I just say m equals 0? We'll get overflows in the other direction now, maybe. Well, okay, so it's the same thing. So I'm already getting activations that are negative. And then they become gigantic. Why? Why? I mean, my inputs are larger than 1, but I thought that wasn't supposed to matter. Like, am I right that -3, and then an overflow is encountered immediately. And then it's like a billion, 4 billion, 4 trillion, whatever. But it's not even supposed to be able to be -3. Could it be that I have implemented softmax wrong this whole time? So 0 is the feature axis. 1 is the batch axis. Let's confirm that. Print x.shape. Um, 80, 50, and then 87, 50. Yeah, so 0 is 80 or 87. So give me the max feature. Then sum along the features. Be the sum of all of the exp of the features is the denominator. The numerator is exp of the features. So how am I ending up with a softmax with a value greater than 1? Or like not between 0 and 1? Google, just answer my question. Can softmax be less than 0? It can never be less than 0. But if we look at mine, it starts, well, at 0.1, which is okay. And then for the next sample, for the next batch, or maybe for the so I guess I don't understand why the second forward is not triggering, or the second backwards is not triggering. Oh, because I don't do the backwards on the front, or like the last backwards. I skipped that one, so I'm only looking at the inner backwards. So we start at 0.15, which is allowed as our activation. That's printed here. So for the first sample in the batch, the first value in the vector is 0.15, which is between 0 and 1. And then the next iteration, it's negative 24 billion. Which is not supposed to be possible. Oh my god, I think I am stupid. Is A the activation of the last layer, not the activation of this layer? How am I doing the training? What am I passing in? Update mini batch. back prop. I'm passing in X. I actually don't know if X is this layer or the last layer. I might have to look at a different backwards function to figure it out. A would be the input to this layer, not the output from this layer. Okay, so what I would want to do here is self.cache equals this, turn self.cache, and then don't use A. Do that. What are the chances? Oh my god, it's working. Okay. Let's kill that. It looks like it's doing something. Clear. Let's remove our debug stuff. I wonder if this would have worked, but whatever. We've got our new way of doing it. This can be 0, it doesn't matter. J.shape of 0 is also known as like A.shape of 0 or D. Off diagonal. Diagonal. I'll call this S for softmax. Okay, how does it work? How well does it work, I mean? Softmax in the middle of the network. Softmax in the middle of the net. So I'm expecting around 49%. Like I said before, it should be not as good as having a ReLU, but it shouldn't hurt it that much, because it serves some of the same purpose as having a ReLU here. And it doesn't like destroy the work that came before it. It's taking a long time to finish a single epoch. Okay, 28%. That's worse than I expected. But it's not 1% and it's not 16%. 1% is when it totally kills learning. 16% is what it was doing before, I think. So I think it's working, but it's hard to say. Yeah, I wish it had been 49%, but maybe a softmax here is more destructive than I thought it would be. What if I add the ReLU back also? I just have a softmax come after it. Would this be closer to 49%? Because I guess I just don't expect that the softmax should hurt that much. It's just scaling the values down. And we know that scaling values down can help sometimes. So I don't know, if it really does hurt it that much, I don't really have an intuition for why that would be. But it could be. That was a lot of effort for what we had to do here. My fingers are crossed, hoping for more than 30%. Validating. About the same. A little bit better, but not up to 50%, which is what I was hoping for. All right, well, I think it's probably working. It's just a little more destructive than I would expect. So softmax, let's say that is done. Okay, Atom is the next thing. I haven't explained what Atom is. Atom is a better way to do stochastic gradient descent. So right now we're doing gradient descent where am I looking? We're doing a momentum-based gradient descent. We've got these velocities. So Atom is just a different variation of a momentum-based gradient descent, except instead of having one momentum parameter, it has two momentum parameters, and they're kind of like first, I don't know what to call it, like first degree momentum and second degree momentum. And so I believe Atom is the state of the art. This is what people actually use when they're doing training. Atom versus SGD. It supposedly has like really trying to just click into the image. All right. Really good performance compared to stochastic gradient descent. So stochastic gradient descent is not even on this graph because it's worse than all of these. And then Atom is the best one here. So we're just going to implement it. I think it shouldn't be that hard to do because it's just the kind of thing we're already doing, but just slightly different formulas. So let's see if that's true. And then I guess we should probably have a parameter for this, or a class for this. What would you call Atom? What is Atom machine learning? It's an optimization algorithm. It's an extension of gradient descent. All right, well, why don't we call it Atom, or sorry, optimizer equals Atom. Beta 1, don't need to specify them because we're just going to use the default values of 0.9 and 0.9999. Okay, optimizer equals Atom, and mu is going to be gone. Okay, how about this actually? Optimizer equals momentum SGD. Mu equals 0.2. So let's start by just re-implementing what we already have as something that can take arguments, or as like something that can be swapped out. So let's make a new file called optimizers.py, class optimizer. I don't know what it looks like. From typing import protocol. Optimizer can be a protocol. We want one called momentum SGD. Def init. It takes a parameter called mu and returns nothing. Self.mu equals mu. And then what's the other thing it needs to do? Okay, so train, you don't have mu anymore, you have optimizer, which is going to be an optimizer. You don't have mu, you have optimizer. Update mini batch. You don't have mu, you have optimizer. And now this stuff is kind of part of the optimizer now. So the velocities could be, when are we setting them? We're setting them all the way up here. These are going to be set instead in optimizer from, or import numpy as np. This stuff optimizer.update. I don't know what you need yet, but we'll figure that out. Def update. And you're going to do this kind of thing. So you need grads. We know what grads is, right? It's a... Here we should, from optimizers, import momentum SGD. Also import Atom and add a no QA. Class Atom. Beta 1, beta 2. That's the default. That's the default. Okay. So I guess you need layer and grads. Mu is going to be self.mu. I don't know what eta and m are. Let's say you get m and eta. How about you get eta and m? Eta m. M is an int. So we end up updating velocities and we end up updating layers. What is a layer? A layer is a layer. From layers, import layer. What is grads? It's some kind of dictionary. That's not the same. I think it's the dictionary part of it. Grads. You are this, I think. Okay, so let's see if this works as well as it used to. It's not crashing. Yeah, I think this should work. This looks right. Okay, we're up to 50%. Nice. Okay, so we're still working as before, but now we can implement Atom. So, you get the gradients. You update this variable called m. So let's do, let's start with the same as before up here. We don't have velocities yet, but I think we're going to have an equivalent thing. So theta is a parameter, right? Yes, theta is a parameter. It's going to depend on m hat and v hat. M hat and v hat are calculated based on m and v. And m and v need to be remembered. So the names they give them are, for m and for v, are biased first moment and biased second raw moment. So I'll just call them first moment and second moment. First moment. And I guess I'll just do second moment at the same time. Why don't I call them moment 1 and moment 2? Okay, so we should initialize these. These are the same as how we did velocities. Moment 1, moment 2. Okay, so then self.moment1 of key. How do you get the new moment? You do beta 1 times, so that's self.beta 1 times the moment that it was before, self.moment1 of key. So let's just do times equals beta 1 plus and this looks really similar to what we were doing before. Plus 1 minus beta 1 times grad. And then moment 2 beta 2 times the previous moment 2 plus one minus beta 2 times grad squared. Okay, then moment 1, I don't know, moment hat, bias corrected moment, M1 equals self dot moment 1 of key divided by 1 minus self dot beta 1 Wait, why do they put a T in the superscript of beta here? With beta T1 and beta T2, we denote beta 1 and beta 2 to the power T. Okay. So I actually have to keep track of how many times I've updated. How does that work? What counts as an update? Is T an epoch, or is T a sample, or is it a batch? Adam, when to update T? Batch versus sample versus epoch. After each batch. Okay. After each batch. So I guess we'll also have to keep track of the T's. It's kind of weird. This is just an int. So once you have the key, let's just say if it's not in T, then self dot T of key equals, does it start at 1 or 0? It starts at 0. No, it starts at 1 because we increment it at the beginning. So I'll start it at 1. Okay, so you are beta to the power of T. T equals self.t of key. I don't need to make a separate variable for that. I can just do that. moment 2, beta 2. When am I incrementing this? I should increment it. Why not u be 0, and I'll increment u right here. Self dot moment or t of key plus equals 1. And then finally, right at the end here, we can do param equals the old param minus learning rate, so that's eta times m1, that's the m hat t, divided by square root of what is this? This is m2 plus epsilon, and I never defined epsilon. Self.eps equals e to the 10 to the negative 8. I don't know if you should have 7 zeros or 8 zeros, actually. Yeah, what is it? Show it to me in the actual decimal form. One, 2, 3, 4, 5, 6, 7. Okay. 1, 2, 3, 4, 5, 6, 7. Okay, so we've got epsilon here. Self.epsilon. So that's Adam. Let's try it out. Optimizer equals Adam. And just use the default beta 1 and beta 2. What are the chances that this works? So if it's about 50%, if it's about 50%, then it at least is as good as the momentum-based gradient descent we were doing. If it's less than around 50, then it's worse. If it's more than around 50, then it's better. After one epoch, that is. So let's see. So I think the thing with the t here, where you're dividing by a beta that keeps growing, is a way to not have to know how many epochs you're going to be doing in advance, because we have that m parameter that flows through. I kind of think, my guess is if you got rid of the second moment, this would be the same as what we were calling momentum SGD. But I'm not sure about that. That's just a thought. Maybe it would be the same if you changed a few things around. Very bad. I mean, it was able to learn, but it was way worse than what we were doing before. going to be pretty hard to figure out why. I'm just rereading it, and it looks like I am doing it properly. I mean, if this is 0.2, I guess I would... If the thing I was saying before that is right, that removing the second moment would make this more like the SGD with momentum that I already have, then setting beta 1 to be the value we were using before, which is 0.2, might bring us back to the same... Oh, wait, we might need to lower our learning rate, actually. Because this is saying 0.001 is a good one, and we have a much higher learning rate. So I'll try that after this. After this fails catastrophically. Actually, let's start writing that right away. Then as soon as this fails, let's try again. Oh, we've also still got regularization, which we may not want. I think atom with weight decay is what this is going to end up being. Okay, so that was worse. What about with a tiny learning rate like we have here? But we have pretty aggressive weight decay right now. So we could try disabling that also. No regularization. Is that the same as not providing an argument? Am I allowed to just not provide one? Yes. I'm crossing my fingers as hard as I can. I really want this to work. Yes. Yes, it seems to be slightly better than what we were doing before. So, and that's with the weight decay. So atom with weight decay. I don't know. I think I'm probably doing it right. I just don't know how much lambda I should use, but I guess I can just trial and error. So I guess the next thing I want to try is no weight decay. This is also just taking so long between attempts. So let's stop this. Very cool. Let's try it with no weight decay. Just see better or worse. By the way, atom, check. It's so cool that we're getting so much of our code to be equal to the state of the art, and we have not had to do anything that hard. Well, especially for atom, this was really easy to implement. Okay. So with no weight decay, it was slightly worse. And then what's the correct amount of weight decay? I don't know. It's too bad because the weight decay kind of cares about the size of the training set. So let's say I wanted to use just the first 10,000 examples. It might not scale in the same way. Is this at least faster? That's not how you do that. You have to use a slice. Okay, that is fast. So 25, 31, 32. We'll kill that. We'll try doubling the weight decay. The score to beat is 25, 31, 32. Does this do better or worse than that? 26, 30, 32. Very hard to tell. Let's try halving it. Will this be better or worse? $25, 31, 30. It's so hard to tell if any of what I'm doing is even making a difference. How about 160? Maybe we're going to find that 40 was already a good amount. $26, 29, 32. It's kind of not making a difference at all, right? Like, how about 10? A little under 25, but now we jump all the way to 32, then 33. So possibly this is better. Really, really, really hard to tell. So I think I'm just going to go back to how I had it, 40. 25, 32. This seems like the best run we've had so far, but who knows? Okay. Actually, why don't we keep this? Because it's nice to be able to go fast. Okay. So we've done some cool stuff. Are we ready to do tensors? That's going to be a big project. Let's just take a look at what's going to have to change. So linear will still have weights and biases. These should be the same shape. It's just the forwards and backwards that has to change. So we'll be able to replace this with an ein sum that's probably pretty straightforward. Yeah. Or at least the matrix multiplication will be pretty straightforward, and then we'll have to figure out how to do a plus here. Okay, so linear will have to change. Why don't we write these down? Tensors. Linear. Layer norm. Activation function should not have to change. So ReLU shouldn't have to change. Oh, actually, yeah, it shouldn't have to change. Softmax kind of has to change. So what did I say? Layer norm needs to change, softmax needs to change. Softmax should be easy because we've already got the ein sums in there. This should have no difference. This should have no difference. So only those three things will have to change. And then we'll need a way to input, but this is the first thing. Inputs should be sequence tokens batch, or probably tokens sequence batch. Okay. All right, why don't we end it here and we'll pick this up next time. Yeah, let's just end it here. Hopefully this was helpful. Thanks for watching.